Something enormous is moving underneath America, and it is not supposed to be there. Seismic waves crossing the region arrive nearly 10% slower than expected, a signature of rock hot enough that geologists don't expect to find it hundreds of miles from any active plate boundary. For decades, scientists blamed an old scar from an ancient continental breakup. That explanation just fell apart. What sits beneath New Hampshire is not a dead leftover. It is moving, drifting toward New York, and roughly 400 miles south, the exact same underground process may have already built a real volcano. When people picture a new American volcano, they picture Yellowstone's restless caldera, or the ice-covered peaks of the Cascades, or the deep-sea volcano off the Oregon coast that researchers have openly debated erupting sometime this year. All three are real, all three are heavily monitored, and all three are exactly where scientists and headlines have trained the public to look. None of them are where this particular story is unfolding. Start with what instruments actually recorded. Seismologists running dense arrays across New England, networks with names like the New England Seismic Transects, Genesis, and a smaller array strung across Connecticut, spent the past several years combining their data with the continent-scale US A-array and Canadian seismograph networks. Together, they listened to earthquakes from the other side of the planet as the waves passed straight through the crust beneath New Hampshire, Vermont, and Massachusetts. The waves came out late, not by much, roughly 10% slower than normal mantle rock should allow. That number matters because seismic speed works like a thermometer. Hotter, softer rock slows sound the same way warm, less dense air bends and delays a sound wave crossing a room. Something down there is unusually hot, and the deeper researchers dug into the data, the harder that heat became to explain away. The feature has a name now. Scientists call it the Northern Appalachian Anomaly. It stretches somewhere between 217 and 249 miles wide, roughly the size of the state of Maine, and it sits about 124 miles beneath the surface, deep in the upper mantle. No one felt anything. No tremors, no odd warmth in well water, no cracked foundations. Families in rural New Hampshire have been driving over it, farming above it, and building homes on top of it for generations, with absolutely no reason to suspect it existed. The ground gave no warning because at the surface there was nothing to warn. That is what makes the location strange. Geologists divide the crust into active zones, where plates grind against each other and produce the volcanoes and earthquakes most people expect, and passive zones, where nothing much is supposed to happen for hundreds of millions of years after a coastline forms. New England sits deep inside that passive zone, nowhere near a plate boundary, without a subduction zone diving beneath it or a hotspot plume rising under it the way Yellowstone has. Most new volcanoes on Earth form for one of three reasons: two plates colliding and forcing rock downward until it melts, two plates pulling apart along a ridge, or a fixed mantle plume burning through the crust above it, the way Yellowstone's hotspot has for millions of years. New England has none of those ingredients. By every conventional model, it should be geologically quiet. The obvious explanation, the one geologists reached for first, was leftover heat. Roughly 180 million years ago, North America tore away from Africa as the Atlantic Ocean began opening. Continental breakups generate heat. That heat, the thinking went, simply never fully dissipated. A scar, cooling slowly, exactly where an old rift once passed. That explanation is reasonable on its face. Rift zones do leave thermal fingerprints that can persist for an extraordinarily long time. But here is where the story stops matching the textbook. When researchers modeled the age, shape, and position of this specific anomaly against the old Africa rift, the numbers didn't line up. The anomaly was too far inland, too oddly shaped, and moving in a way a fossil scar has no business moving. A static leftover does not travel. This one has. In 2025, a team led by geologist Thomas Gernon published new modeling in the journal Geology, and it rewrote the anomaly's origin story entirely. The heat wasn't inherited from Africa's breakup at all. It traced back to a different, more recent rift, roughly 80 million years ago, when Greenland tore away from North America and the Labrador Sea opened between them. That event happened over 1,000 miles to the northeast, which means this hot mass didn't form under New Hampshire. It arrived there. 80 million years after its birth, it is still on the move. Jernin has called it one of the most puzzling features in North American geology, a feature that sat unexplained for so long, partly because nobody expected an 80-million-year-old rift from the opposite side of the continent to still be shaping rock this far inland. That is the detail that breaks the old story completely. This isn't a stationary relic anyone can safely ignore. It's a moving front, still drifting southwest through the mantle at roughly 12 miles every million years, having already traveled well over 1,000 miles from where it began. And the natural question the researchers had to answer next was simple. If it isn't sitting still, what is actually pushing it? When the study became public, headlines around the world seized on it, describing a giant hot blob invading New York, as though the city needed to start bracing for something. That framing oversold the urgency. 15 million years is not a warning. It's closer to the pace at which entire mountain belts rise from flat ground, but strip away the exaggeration and a genuinely strange fact survives underneath the coverage. Whatever this thing is, it did not stay where it started, and it has not finished moving. Test the leftover heat idea properly, and it collapses on distance alone. No stationary rift scar migrates 1,100 miles from its point of origin over tens of millions of years. Whatever mechanism is responsible has to explain motion, not just heat. That ruled out the simple version of the old theory and forced researchers towards something stranger, an active, ongoing process, not a one-time event fossilized in the rock. The mechanism they landed on is called a mantle wave, and it starts with something breaking. When a continent rifts apart, the thick, cold base of its lithosphere becomes unstable right at the edge of the tear. Chunks of that cold, dense root eventually give way under their own weight and sink into the softer mantle below, one after another, in what geophysicists call a Rayleigh-Taylor instability, essentially dominoes falling in slow motion, each one triggering the next. Each drip that sinks pulls hotter material up to replace it. That upward surge of heat is what shows up in seismic data as a slow zone. And because each drip triggers the next one further inland, the hot pulse doesn't stay where it started. It walks across the continent over tens of millions of years, one collapse at a time, the way cold syrup sinks unevenly through warm honey, each pulse nudging the next one forward. Here the story widens, and this is where it stops being a curiosity confined to New England. If a mantle wave from the Labrador Sea produced the anomaly under New Hampshire, it should have left earlier drips behind it, further back along its 1,000-mile path. Researchers went looking, combing older seismic data sets for a second signature. They found one. A second, older thermal anomaly sits in the upper mantle beneath Virginia, roughly 200 miles to the south. It's called the Central Appalachian Anomaly, and its estimated age, around 135 million years, lines up almost perfectly with the earliest stages of that same Labrador Sea rifting. A separate 2024 study using the New England array found something just as telling directly above the younger anomaly. The lithosphere up there has been measurably thinned, as though something below has spent millions of years eating away at its base, weakening the very layer that normally keeps deep heat from getting closer to the surface. Researchers admit the chain might not stop at 2. Seismic coverage further north toward Newfoundland and the Gulf of St. Lawrence, close to where this entire process may have first begun, remains too sparse to say for certain whether even older drips are sitting there, simply never mapped. Now ask what an earlier drip in that same chain might have done once it reached Virginia tens of millions of years ago. The answer is not hypothetical. Virginia has real volcanoes, 2 of them to be exact, sitting quietly in the Shenandoah Valley. Mole Hill, a tree-covered mound west of Harrisonburg, and Trimble Knob, nearby in Highland County. Both are built from basalt dated to roughly 47 to 48 million years old, making them among the youngest volcanic rocks anywhere on the entire east coast of the United States. NASA's Landsat satellite has photographed Mole Hill from orbit, an unremarkable forested rise in the middle of farmland, nothing about its surface hinting at what it actually is. What it actually is, according to geologists, is the eroded plumbing of an active volcano, a hardened conduit that once fed a real cinder cone eruption, basaltic magma punching upward through layers of ancient limestone. One researcher studying the region has described the magma there as reluctant, only breaking through where the crust already offered it a weakness to exploit. Researchers have since identified nearly 100 smaller volcanic features scattered across Virginia and West Virginia from that same period. an eruptive episode that ran from roughly 48 to 35 million years ago, far from any plate boundary, in a place with no business erupting at all. That should feel unsettling because it means this isn't theoretical. The mechanism now suspected of driving heat toward New York already produced real lava, real ash, real eruptions in the very state sitting along its earlier path. But slow down before drawing the obvious conclusion, because the connection between Virginia's volcanoes and this dripping mantle process is not settled science. Geologists still disagree about what actually triggered Mole Hill. One leading idea holds that the ancient thickened root beneath the Appalachians in Virginia simply grew unstable after heating for hundreds of millions of years, then dripped away roughly 50 million years ago, displacing magma upward along old fault weaknesses. That's essentially the same drip mechanism now proposed for the anomaly chain, but a competing idea points instead to a thin, weakened strip of crust running from around Missouri to Virginia, a rift that started forming and then failed before an ocean ever opened. Typical rift magma runs around 2,400 degrees Fahrenheit, and Mole Hill's chemistry, a mix of basalt with small traces of more evolved rock types, doesn't cleanly match either explanation on its own. The honest answer right now is that more than one mechanism remains plausible, and researchers haven't fully closed the case on a 50-million-year-old volcano, let alone the anomaly still active today. Still, line the pieces up and a pattern appears that is hard to dismiss. An older thermal anomaly under Virginia dated to the earliest phase of the Labrador Sea Rift. A documented volcanic eruption in that same state tens of millions of years later from a mechanism that plausibly matches the drip process. And now a younger, still active version of the identical anomaly sitting under New England today, actively migrating toward one of the most densely populated regions in North America. That comparison deserves to land with weight, and it should, but it also needs limits immediately because similarity is not a forecast. The anomaly under New Hampshire is roughly 124 miles down, diffuse and spread across hundreds of miles. Nobody has drilled into it, sampled its rock, or confirmed liquid magma anywhere near it. It is nothing like Yellowstone's shallow, concentrated magma chambers, and nothing like a volcano actively building toward eruption. What scientists have measured is heat, inferred from the speed of seismic waves, not molten rock rising toward the surface. Current models suggest the center of this anomaly will keep drifting and reach beneath New York over roughly the next 15 million years, at which point the crust above it is expected to stabilize rather than erupt. 15 million years is longer than modern humans have existed as a species many times over. That number is not a countdown to disaster. It's a geological forecast on a timescale where entire mountain ranges rise and erode away. So the parallel with Virginia teaches something narrower than it first sounds. Given tens of millions of years and the right kind of thinned, weakened crust already sitting above it, this type of deep mantle drip has, at least once, coincided with real basaltic volcanism reaching the surface far from any plate boundary. Even in that best documented case, the eruptions were small, a cinder cone here, a lava-capped hill there, nothing remotely resembling an explosive, ash-choked super eruption. It does not mean New York is destined to repeat Virginia's history. It means the mechanism is real, it has already happened once nearby, and scientists now have a documented reason to keep watching closely instead of assuming the region is geologically dead. And the watching has already produced something new. In March of 2026, researchers from Yale presented preliminary findings at a regional geological meeting describing seismic evidence consistent with vertical flow inside the anomaly itself, movement not just sideways but upward near its center. The result hasn't been fully published or independently confirmed, and the researchers involved are treating it cautiously. But if upward flow is really happening, it would mark a meaningful shift from a mass of hot rock simply drifting along with the mantle to one that may be actively rising within itself, the same kind of internal motion that, in other systems, has sometimes preceded material moving closer to the surface. Alongside that, a newer high-resolution model published in 2026, built from denser regional seismic networks layered onto the continent-scale dataset, has given scientists their sharpest image yet of the anomaly's actual shape and boundaries, replacing decades of blurrier, lower-resolution guesses. That leaves one real unresolved question hanging over everything else. Is this thing simply drifting the way it has for 80 million years, or has something changed recently enough to matter? Nobody can answer that yet, which is exactly exactly why the instruments stay in the ground. So separate what is actually known from what remains open. Confirmed. A real, physically measured zone of unusually hot rock exists deep beneath New England. It has been migrating southwest for roughly 80 million years, and the crust directly above it has been measurably thinned. Confirmed separately. Virginia has two genuine dated volcanoes from a geologically similar setting, tens of millions of years after an earlier version of the same anomaly likely passed beneath it. Interpreted, not confirmed, that a shared drip mechanism links those two facts together, and that the same process could someday, over an inconceivably long timescale, produce comparable volcanism further north. Still unresolved, whether the newly reported vertical motion is real, what it would mean if confirmed, and whether more of these buried anomalies exist in the gap between Virginia and New Hampshire, hidden simply because that stretch of ground hasn't been instrumented as densely as either end. What would actually change this assessment isn't vague speculation, it's specific. Denser seismic coverage across the mid-Atlantic states in Pennsylvania, Maryland, and New Jersey, filling the geographic gap between the two known anomalies where almost no dense array has ever been deployed. Heat flow measurements from deep boreholes, verifying the temperatures inferred from seismic speed rather than assuming them, and confirmation, one way or the other, of whether that reported vertical flow holds up under independent analysis. Any one of those findings could sharpen or completely rewrite the current picture. And if the mechanism ever did repeat itself the way it did in Virginia, geologists say the result would most likely look nothing like a headline-grabbing eruption. A small basalt vent, a modest cinder cone, the kind of feature that could sit quietly in a field for millions of years before anyone bothered to date the rock. None of that amounts to a countdown. Nobody studying this anomaly is forecasting an eruption under New York, this decade or this century. What they are forecasting is 15 more million years of a slow drift southward, a process already caught once in Virginia, quietly reaching the surface as a real volcano, while nobody was watching closely enough to notice until the rock had already cooled. For now, the work is patient and unglamorous. Seismologists reprocess old earthquake recordings from around the world, hunting for fractions of a second of delay. Geophysicists compare this year's tomography model against last year's, looking for any shift in the anomaly's outline that older, blurrier images couldn't have caught. None of it makes for a dramatic press conference. All of it is how a slow-moving mystery like this one actually gets solved, one seismic wave at a time. Which brings the story back to where it started, to the instruments still listening under quiet New England ground. Somewhere beneath New Hampshire farmland and Vermont forest, seismic waves keep arriving just slightly late, still tracing the outline of something enormous and hot that has been crossing the continent for 80 million years and has no intention of stopping. 200 miles south, in a low, unremarkable hill outside Harrisonburg, the same process already finished what it started once before. The ground above both of them looks exactly the same, ordinary, quiet, and utterly undisturbed.